Welcome to today's webinar, Virtual Reality, where humans, data, and artificial intelligence meet, with Caltech Professor Djorgovski. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You have joined the presentation and listening using your computer speaker system by default. If you prefer to join over the telephone, just select telephone in the audio pane and the dial-in information will be displayed. During the last 10 minutes of the presentation today, Professor Djorgovski will answer questions from the audience. You may send in your questions at any time during the presentation by typing your questions into the questions pane of the control panel, and we will address them during the Q&A session at the end of today's presentation. I would now like to introduce our speaker for today, Professor George Djorgovski. Dr. Djorgovski is a professor of astronomy, as well as the director of Caltech Center for Data-Driven Discovery. He has studied a broad variety of topics in astronomy and cosmology, including the fundamental properties of galaxies and their evolution, gamma-ray burst, and dark matter. And he has also led several large digital sky surveys. He is a co-founder of both the Virtual Observatory Framework and Astroinformatics, an emerging discipline that lies at the intersection of astronomy, computer science, and information technology. Dr. Djorgovski spends about half of his time on the development of computational, mostly data-driven science. He is currently investigating the ways in which computing is fundamentally changing how we approach science, scholarship, and education. Without further ado, I'll turn it over to Dr. Djorgovski.
Thank you. Good afternoon. Thank you all for listening. Today, I'd like to tell you about some of the important trends that we're seeing in science and elsewhere. I've been already introduced to you, so I won't repeat that. But general question here is we have now big data. They're very fashionable, and they're really changing the ways in which we do everything, including science and scholarship and business and security and so on. And people obsess about size of the data, how they're growing exponentially. That's true. But in any case, the data are no use if you can't extract some useful, actionable knowledge from it and do that in a timely fashion. So it's not really all about data. It's all about knowledge discovery. Now, machine learning is another fashionable topic. It's a component of machine intelligence, and that lets us analyze these large, new, complex data sets and find structures and patterns in it. It could be correlations and groupings like clusters and anomalies or outliers and so on. And there are many, many good algorithms to do this. But one thing that you always have to remember is you have to see what you're doing. Because, for example, if your algorithm assumes that your data are all like Gaussian normal distribution and data don't look anything like it, you'll get misleading or wrong results. So this is a case of not garbage, but good data in, but garbage out. Not because anything's wrong with the data, but because you chose the wrong algorithm. So you have to visualize the data first to clean it, to understand how to analyze it throughout the whole discovery process, and finally to understand the results and to present those results to someone. So this is where the key challenge of data science is, I think. Now here is a cartoon. I'm plotting here schematically a three-dimensional cube, but imagine that it doesn't have 3, but 300 or 3,000 dimensions in this data space. Every quantity you measure for something, every column of your spreadsheet, if you want, is a new dimension of a data space. And it could have, say, thousands of dimensions. Now, data fill up the space in some strange fashion, need not be nice, and you don't necessarily know how. And then there are gaps in the data and missing data and wrong measurements, and so you have to clean it again, visualizing things. But the important point is that there could be some interesting structures, something that you didn't know about it in this data. This is why you got the data itself. Let me give you just an example of what that might look like. Suppose that there is a pharmaceutical company and they're testing new cancer drug. And they find out that, yeah, it's effective in about 1% of all cases or a little less, so not really worth developing. But they have the data on many, many patients, and data include clinical data and demographic data and their genetic data, and all these data can form large dimensionality, thousands of dimensions parameter space. And it still turns out In one particular corner of this gigantic data space, in one particular set of these data dimensions, there is something important. The drug is 100% effective for those patients, like say, for example, particular age or ethnicity or some environment and so on and so forth. And so, of course, for them, it will be life-saving. So this is why we need to be able to explore these high dimensionality data sets to find those hidden gems in them. Whereas, data mostly maybe just noise, but somewhere there is something exciting and you have to find it, and you have to find it in this highly dimensional space. So this is the way to think about it, that the real challenge is not data size, because the computers also improve exponentially, according to Moore's law, but data complexity. We're measuring and collecting more different kinds of things. You can imagine demographic data or commercial data. And so each of the things that you measure is a new dimension of the data space. And so how do you see what you're doing? How do you choose the algorithms? How do you understand the results of these algorithms? We can certainly see in 3 dimensions. With various tricks, we can represent up to 10 or 12 dimensions, although for most people they would saturate at about 8. What I mean by this is you always have X, Y, Z coordinates, but you can use shapes and sizes and colors of points and transparencies and put little textures on them and whatnot. So you can actually visualize as many dimensions as you want, but you stop understanding what's going on at about 10 or 12. Nevertheless, that's a lot better than 3 or 2 or 1. And there is a premium on being able to visualize a large number of data dimensions at once. In any situation where you have multiple variables interacting, you have multidimensional data space. And if you project it to any one of those axes, you're losing information. You just miss all the patterns. So this, I think, is really the key challenge of data analytics today. How to represent high dimensionality of data sets, modern data sets. So that's the challenge that we're facing. You really can't discover any knowledge unless you can see what's going on in your data. Humans have fantastic pattern recognition system in their heads, and we feed that pattern recognition system through visualization most of the time. So you never really understand anything unless you can visualize it. Now, unfortunately, that's a problem. So here is your typical spreadsheet, and you can do one-dimensional plots like histograms or pie charts, or you can do two-dimensional scatter plots of X versus Y, and most of the programs that can do 3 dimensions do a terrible job. But that's about it. And so every time you have more than 2 columns in your spreadsheet, you really need something more powerful. If you have thousands of columns, you can be spending years and years looking at everything separately and still not discover interesting phenomena that are hidden in the space. Now, let me switch the gear a little bit. Virtual reality and augmented reality, I'll just call them virtual reality for short, are really rapidly developing technologies for humans to interact with computers. And they're part of an evolutionary trend. First, large computers using paper cards or tapes or whatnot, and then that evolved into desktops, and now mobile computing is everywhere. You have a supercomputer in your pocket. And the next stage is probably something that will let us go into multiple dimensions of cyberspace and overlay data, make data fusion between real world and the data space. As the technology improves, things have been changing in systematic fashion. First, the computing power, obviously, and then also how usable and intuitive and friendly and how high quality information you're getting and the rate of it. So many people believe that some form of VR, AR, not with the clunky headsets that we have today, but with something as lightweight as normal glasses or smart contact lenses, will be the next platform how we interact with computers and with the world of information behind them, like web, for example. Another interesting thing about VR is it's naturally a collaborative space, and people who play multi-user or multiplayer games know this very well. And so it can enable collaborative data exploration and discovery. It also solves many of the technical problems from traditional visualization, like occlusion of points and perspective navigation. And best of all, it leverages a multi-zillion dollar investment, that's a unit, by the games industry, because we would never be able to develop these miracle devices on our own. However, games industry makes a lot of money and they really want to improve this technology. And so we'd like to see how we can use it for something other than games and entertainment. Now, our friends at JPL have created Virtual Mars. I don't know if you know about it, but Scott Davidoff and Jeff Norris and their collaborators collected the data from Mars rover and orbiters around Mars and created three-dimensional Mars terrain. And so then you put headset on and you're standing on Mars next to the Curiosity rover. And your colleagues can be there represented in this ghostly form. So the way that scientists could drive the rover, decide where to go, is they look at panoramic photography and decide, well, this rock over there looks interesting, let's go there next. And so this team divided them in two groups, one that did the same thing they always do, and the other one that was doing it in virtual reality, and they gave them a test to estimate relative distances and positions of different features in this 3D landscape. People doing it in virtual reality turn out to be 4 times better in making those estimates than people using the traditional approach. And so for the last couple of years, Curiosity rover is actually driven in virtual reality, if you didn't know that. So that illustrates also a great gain that can be made using this new way of representing data. So here are some typical data plots. This was done by some of our students, Sarah Ganup and Subin Lee. And on the left, you see typical projections, X versus Y, X versus Z, and you see something's going on. On the right is just a snapshot of the data cube in 3 dimensions, where machine learning has identified 5 clusters that you simply could never, ever see in traditional projections. And this is about as simple as it gets. So scientific literature is full of diagrams like these. These are real data from some astrophysical set on quasars, and they're really from a 6-dimensional data space. So you plot one versus the other, you see something's going on, but there are about 15 different plots that you can make, and so it's kind of hard to keep track of what's happening. Now, this is what happens in virtual reality. I'm showing you a little video where we use XYZ positions and colors and shapes and sizes and transparencies to encode these 6 dimensions, and you plunge into your data space, and instantly you can see the outliers and query the points and find out what are these anomalous points. And you also instantly get a much better intuitive sense of the overall geometry, how data are distributed. And you can see that there are 3 big clusters and they don't have nice shapes. So this is just one of the early examples we've done. A product of this work was a Caltech JPL startup called Virtualytics, which is now commercializing this technology and is getting great traction in a number of industry sectors, finance industry, defense, and so on. Because once you start doing this kind of stuff, you never want to go back to the traditional spreadsheet graphics. And the interesting point is that we combine machine learning and data visualization inside the same virtual space, shared space. So multiple users, collaborators, they can be physically in different sides of the world, like in Pasadena and New York and Tokyo and Singapore, but they share the same virtual space and interact with each other, interact with the data, and interact with machine learning tools to analyze the data in a kind of smooth fashion. Here's just an example how that might look like right now. The users are represented as these very schematic avatars, but someday they'll be fully photorealistic representations of real people you can recognize. And you can query the data through the machine. Machine learning can find patterns that will direct your inquiry. And overall, this is all moving towards truly smooth, iterative, collaborative human-computer discovery of patterns in highly dimensional, highly complex data. All kinds of visualizations can be done. The network visualizations, which are popular for studying social media, for example, whenever they are projected in any flat screen, you lose the structure, and instantly in multidimensional space, you can see how it is. You can overlay abstract data on top of geographical maps or globe and manipulate them around, move the data, see what's happening, and look at models of the data as well as the real data, and understand why some algorithm is telling you a particular thing and why it deviates from what you expected. So the collaboration part is really important and underappreciated. We found, and many other people have found, that interaction inside virtual reality is way more intuitive and feels more natural than any flat screen video conferencing application. And the reason why this works so well is that we are optimized by the evolution to live in a 3D world and interact with 3D objects and with each other in 3 dimensions. And so virtual reality is giving us a step in that direction, and it triggers better our pattern recognition, our communication with the others, and really it's emerging as probably the best telepresence platform we ever had. Now we continue to work with this, and this is work with Santiago Lumbeda and Matt Thompson and Mitch Gutman. Thompson and Gutman are professors in biology. And here they visualize 3-dimensional structure of DNA molecules, or protein molecules, and you can interact with it and find out traditional database what's happening with a particular strand or what have you. Now I'm showing another little video, which is manipulating another data set. This is from Matt Thompson. Data points represent different genetical data that are derived through his analysis. And you can instantly find out how the different subgroups are distributed. You can isolate the interesting ones and study them further and so on. Or you can bring in the data cloud and plunge into it. And once you're inside the data looking out, you get a much better sense of what's happening than when you're outside of the data and looking in. Another data set we worked with Professor Sternberg in biology, and this is data on a worm called C. elegans, which is favorite of many biologists. And here we have 3-dimensional model of this organism with all of the subsystems, digestive, nervous, and so on, and interacting with the 3D model and with the representations of the data in a traditional web display. And so you can just have it in desktop version, you can have it a room size, or you can throw it out of the window, virtual window, of course, and becomes size of a whole building. And then you can bring it in if you want, slowly. And particular subsystem, I don't remember which one is being visualized here. You can get inside this cyber worm and look at things in much more detail. And you can then, of course, change the perspective and have a much better understanding of how these structures inside this organism are changed. You can change to which subsystem you're looking at and so on. So biologists will probably find this kind of tool, but also in medicine, this kind of tool to be very useful. Another project we're working on right now involves virtual teaching labs. Why do we do this? Well, labs are an important part of learning process when you do things, in hands-on fashion, learning by doing. But what you can do in virtual reality, if you represent whatever you're studying, molecules or physical systems, inside this created synthetic space, you can do things that are impossible in real life. You can shrink down to the size of molecules and enter the molecules. You can expand yourself to be bigger than Milky Way galaxy and look at the galaxy from the outside. And also, if you are doing engineering labs, say you're making a nuclear reactor and it melts down, nobody gets hurt. Or in your chemistry lab, if your apparatus explodes, again, nobody gets hurt. And the best of all, Caltech students can do this at 2 a.m. in their dorm room, which is, of course, where Caltech students do all of their work. So we think that this will be very interesting and practical and attractive. And it's also the kind of the missing link from the online education, things like MOOCs that can deliver a lot of content in a very scalable fashion, but they're missing both the human interaction component and this ability to actually do hands-on learning in whatever subject you happen to be working. So here is just a prototype of a virtual classroom that some of our SURF students have been building over time. You can imagine that instructor can be giving a lecture and students can have different buttons on their virtual desk. And if they don't really understand something, but they're reluctant to show their ignorance to their colleagues because of course they'll be ashamed for life, well, then they can just send that signal to the instructor. Instructor can see, oh, looks like half of my class didn't understand what I just said. And so they can repeat and do things like that. And of course, you can virtual labs in adjacent to this. Now let's turn over to the machine intelligence. And this is not something new. We've been using different forms of machine intelligence for decades now for data analysis, to explore the complex data, to explore large quantities in data, tedious tasks that humans just couldn't do. But the interesting part is that as the data quality and complexity arises, they probably contain structures that are meaningful and important in many dimensions, and they exceed the capacity of human brain to grasp. So what do we do then? Well, we can use AI or machine intelligence to help us discover things in spaces that we cannot see, but machine can, and moving more and more towards collaborative human-computer discovery, or as I like to think of it, is we move from information technology to the cognition technology. Well, here is one slide history of machine intelligence. It starts, of course, with Alan Turing of Turing test, which published this paper in 1950. 10 years later, JCR Licklider, you probably never heard of him, but he was a DARPA program manager, published a visionary paper, Man-Computer Symbiosis, in which he foresaw all of this but didn't have the technology. And by the way, you can thank him for the existence of the internet because he was the one who funded the first university projects to develop the basis of the internet. And already in the 1990s, scientists started using machine learning tools to analyze large data sets. Google started in the late 90s. Every time you do a query on Google or one of the other search engines, you are talking to machine intelligence that somehow knows what are you looking for and can disambiguate them. And important milestone in 1998 was that computer beat Garry Kasparov and became world chess champion. And up until then, skeptics were all saying, oh, but computers will never be able to beat humans at chess because it's such an intuitive game. Well, too bad. This has been going on now for 20 years. Now we started interacting with machine intelligence using just human voice, natural language, and like you can talk to Siri or Cortana or Alexa or what have you. And there is a big machine intelligence machinery behind them, which is how they know what you want. A really important milestone 2012. But here is the really interesting one. In 2016, computer became the Go champion. Go is an ancient game that is supposedly way more complex than chess. I don't know, I'm not a player. And for the first time, the machine was able to beat human champion, which was completely unexpected by the Go community. And then a year later, They just shown machine intelligence the rules of the game, and it invented its own strategies and beat the previous machine learning champion. So we really are moving to human-computer collaborative discovery and to cognition technology. Now, here different snapshots from news reporting this. And by the way, the machine that became Go champion just they showed the rules of chess and became world chess champion, beating previous computer in just a few hours. Now the title from an article I circled in the lower left is the really important point. Machine intelligence discovered new strategies for the game that humans have missed for past 2,000 years or so. And this is really important. We're not building these machine intelligences to do the same thing we do. No, we want them to think different from us and complement us in the ways that we simply cannot do. So I, for one, wish to welcome our new machine overlords. And Hollywood has been warning us about this for a long, long time. And connoisseurs of this genre know that the one on the right is the most dangerous one of them all. But a couple interesting points. First, the fear of machine intelligence. The second, that we anthropomorphize it. We always put it into humanoid, human-like robot. Now, I'm an optimist, and I think that Skynet will not become alive, and that instead, we're going to do something more interesting. So essentially, what we have done on this planet is to create an alien intelligence, which is different from ours. And this is something you cannot uninvent. And it's going to get better and better and better. And so what's the best way by which we can interact with machine intelligence, aside from asking Siri questions or typing in a Google box? So we'd like to achieve symbiotic relationship with machine intelligence, really working together, using it to expand our abilities, just like we've done with all of the technologies so far, from grasping sticks and stones, cars and airplanes and computers and so on. Well, this may or may not always work, but we're trying to find out how we can actually interact with this new alien intelligence that we created in an optimal fashion. Well, it turns out that actually virtual reality may be an optimal platform where carbon-based brains and silicon-based brains can interact and do tasks together. It is the most intuitive interface so far, and we'd like to anthropomorphize it so Siri can now have avatar and can talk to her avatar, or not Siri necessarily, but you can imagine the astrophysics machine intelligence helping researchers find out things in our complex data. This, I think, is probably another 5 to 10 years away. So essentially, visualization in any kind form is really where the human minds and data analytics, machine intelligence meet and interact. And by far the most powerful platform that we found so far to do this is in virtual reality. Virtual reality is still in a primitive stage, mind you, but it's getting rapidly better and better. And in a few years' time, you'll think nothing of it. Like now, you just think nothing of pulling a supercomputer from your pocket and calling your relatives or looking at pictures of cats or arguing with some idiot who has different political opinion from you. So to look ahead, and by the way, did you know that you can buy a crystal ball for about $15? Who knew that telling future is so easy? I see that trends are clear. That first, the VR will become more pervasive, VR or AR. And it's now driven by the entertainment industries, but many others, everybody else will follow. And we need to provide tools to do serious stuff with it and not just play games. And Moreover, the current generations of digital natives who are grown up playing online games, for them, this is the most natural thing ever. And they would actually expect to be able to interact with computers and data and knowledge in this fashion. Now, the second big trend is that artificial intelligence is become more and more pervasive, and it's helping us a variety of tasks, whether it's booking airplane tickets or finding answer to some trivial question, but also in science or maybe business intelligence or security as a tool to find quickly some interesting, actionable knowledge. And so we think that virtual reality is really the optimal platform that we have so far, in which the two can be united, and that together, that machine intelligence and this new way of human-computer interaction will form what I call the cognition technology. So with that, I'll stop and I'll be happy to answer any questions you may have. Thank you.
Thank you, Dr. Djorgovski. We're now going to begin answering the questions submitted during today's presentation. As a reminder, you can still submit questions through the questions pane in your attendee control panel. Dr. Djorgovski, our first question is from Jeffrey, and he asks, how does the spatial resolution of VR displays limit data visualization? What strategies can be used to overcome limited pixel densities?
Well, that's a matter of developing better hardware, display hardware, and just about every electronics firm in the world is trying hard to do that. Of course, you want to have as many pixels as you possibly can, and current headsets are a little limited, but there's strong drivers to have many more pixels. I'm not conversant with the actual display technology, so can't really answer that. But I expect that the fidelity and refresh rates and so on will be improving dramatically because of their commercial drivers.
Excellent. Thank you, Doctor. Our next question comes from Scott, and Scott is asking, why call machine property intelligent when the recognition of structure in data is dependent on mathematical models are ultimately a product of human input?
Well, that's a good question. And yes, humans create models, but models can be so complex. We can create a recipe for a model algorithm, and the output of the algorithm may be too complex for us to understand. The definition of artificial intelligence is something that people have been battling for decades now. Somebody said, asking if whether computers can think is like asking whether submarines can swim. Well, they do perform some sort of intelligent function, but different from us. And I think that's the key point that we keep forgetting. It's not about replicating what humans do, but really amplifying our ability to see things which we otherwise never be able to see.
Thank you, Doctor. Our next question comes from James. He asks, besides aiding humans, can VR aid AI in its own operation and effectiveness?
I'm sorry, can you repeat that?
Sure. Besides aiding we humans, can VR aid AI and its own operation and effectiveness?
Probably not. I mean, VR is all about interface between humans and information. And information usually through some visualization, although we're talking about using sound, data sonification, and so on. And so it's really for the benefit of the humans. How do we wrap our own pattern recognition system, our intuition, over quantitative content of the data? And that's where VR is really helping us. Machines don't see, but they do think in their own way. And that's just fine.
Thank you. Thank you, Dr. Djorgovski. Our next question comes from Joseph. He asks, how long do you foresee until a credible individual AI will become available, and one that is not tied to the cloud for AI processing, but instead will be a standalone and secure personal assistant?
Um, well, first of all, I have no idea. Second, you have to decide what do you mean by really machine intelligence that will pass the Turing test. For that matter, I know a number of people who cannot pass Turing tests, but that's a whole another story. Uh, it is certainly a matter of compute power, but as you know, that's been increasing dramatically, and there is no reason why should we demand something to be really independent from cloud or next generation cloud. With the Internet of Things, there'll be one gigantic, highly complex information tissue creating this cyberspace backbone to everything we do, just about everywhere you go.
Thank you, Doctor. Our next question also comes from James. James, as the extreme, the advantage of humans and an AI VR relationship is intuition and leaps of understanding. Can we expect AI to become intuitive?
It's a great question, and I don't know. I would say most people would say no, but then of course we can't predict what really advanced forms of AI will do. And this is what I meant really by symbiotic relationship, that we do have intuition and creativity and so on, which is really hard to reproduce in machines today. So we are amplifying our abilities and things that machines can do. A pocket calculator can calculate better than you can in your head, and we outsource our collective memory to Google anyway. So I think there is certainly a place for humans in the discovery process, will be for a long time to come, but I simply cannot possibly predict when machines will have properties that you would call intuition or creativity.
Thank you, Doctor. Our next question comes from Hugo. Should we be concerned about political or economical dominance using AI?
Well, like any other technology in the history of the world, yes. In fact, our president Putin said whoever rules AI will rule the world, or something like that effect. I don't think so, but certainly it is a strategic technology, just like computers were. But the cat's out of the bag, so it will not be hidden by the or owned by the governments. We all can read news and see how all these things are happening. They're certainly changing the way politics is done and the warfare and everything else. Let's just hope that we can control things in a smart enough fashion. We did manage not to kill ourselves with nuclear technology so far, so hopefully we'll continue that positive tradition.
Thank you, Doctor. Our next question comes from Linda. How does your work on astronomy influence your work on data science and vice versa?
Well, good question. I mean, I got into data science because of the big data in astronomy. It's one of the first digital sky surveys when I and others recognized that this is something new, that there's a quantitative change moving into a qualitative change, and that the old tools that we've been using to analyze the data are simply not adequate. So this is how I first started using machine learning to analyze the data in the early to mid 90s. And then the exponential curve of Moore's law keep going and going, and we started to understand that we really need to harness all these technologies that produce the data to help us deal with the data. So this is what virtual observatory framework was supposed to do. And then I started thinking, well, this is not peculiar to astronomy. Every field of science will have exact same problems. And what we see is really the emergence of new scientific methodology for the data-rich, computationally enabled science in the 21st century. And just like other things have been added to the scientific method in the past, say statistics, which was added as part of the scientific method to help us deal with, I don't know, kilobytes of data. Now we need something else to help us live in a petascale world and beyond. And as we do this, we then build new tools. They're all based on stuff that computer scientists have done many years ago, but they haven't been applied yet. And then we apply those new tools to analyze data from our current sky surveys. So it's been a very good virtuous cycle there. But what really motivates me is just understanding how is this technology changing the way we do science and scholarship in addition to everything else.
Thank you, Dr. Djorgovski. Our next question, in your opinion, how do you think advances in virtual reality will change the way we conduct science?
Well, it's a platform, and just improving quality of the display and interaction capabilities inside virtual reality, which should be done for other reasons, is what we need in order to interact with the data more effectively. So this is like asking in the early 90s how would the Windows technology change the way we do science. It's part of the technology that we will use every day.
Thank you, Dr. Djorgovski. Our next question comes from Conceto, and he asks, do you think consciousness plays a role in the future application of AI?
Well, I'm not sure how to understand this. If you mean, are we going to mimic what humans do in their minds? Probably not. Maybe just for experimental purposes. So I'm not really sure what you meant by that. If you mean will the machines become self-aware in some sense? Yeah, probably will. And in not too distant future, I would say, although limited in their capabilities. And hopefully we will always be able to pull the plug.
And thank you, Dr. Djorgovski. We don't have any more questions in our question box right now, so I would like to say thank you to Dr. Djorgovski for leading an engaging and informative discussion today. And thank you to all of our participants for attending today's webinar, Virtual Reality, where humans, data, and artificial intelligence meet. Once you leave today's webinar, you'll receive a survey on the presentation, and we would appreciate it if you can complete that and provide your feedback. You will also receive a follow-up email within 24 to 48 hours with a link to view a recording of today's webinar. And on behalf of Caltech Alumni Association, thank you for joining us today and have a great rest of your day.